Hello everyone, myself Shrasti Srivastava. My roll number is 39 and today we are going to discuss the topic motion on a plane and central orbit with applications to Kepler's law. So let us begin with motion on a plane. Let us suppose the position of particle on the curve at any time t be p x comma y. So this is the curve, this is point P where the particle is placed whose coordinates are x and y with arc length s. So this is the arc length which is named s measured from a fixed point p1. This is point p1. Let v be the velocity at p. So at p the velocity of the particle is v and x, y are the components of forces acting on the particle along coordinate axes. A normal reaction R acts at p on the particle because the curve is smooth. So on resolving the forces along the tangent at p, the motion is given by mv dv by ds equals x cos psi plus y sin psi, and this can be named as equation 1. But from this diagram we can say cos psi equals dx by ds and sin psi equals dy by ds. Then putting these values in equation number 1, we get mv dv by ds equals x dx by ds plus y dy by ds. Now on integrating with respect to s, we get integration of mv into dv by ds into ds equals integration of x dx upon ds plus y dy upon ds into ds plus c1. Here c1 is the constant. So half mv square equals integration of x dx plus y dy plus c1. So this can be equation number 2. Now let us take x dx plus y dy equals phi x comma y. So capital X becomes del phi by del x and capital Y becomes del phi by del y. Then we have half mv square equals integration of del phi by del x into dx plus del phi by del y into dy plus c1, which is equal to integration of d phi plus c1. So half mv square equals phi x comma y plus c1, and this can be equation number 3. Hence phi x comma y is known as the work function and half mv square gives the kinetic energy of the particle at p x comma y. Now let initially the particle of mass m starts the motion with velocity v0 from the point p1, that is x0 comma y0. Then equation 3 gives half mv0 square equals phi x0 comma y0 plus c1, which is equation number 4. From 3 and 4 we have half m v square minus v0 square equals phi x comma y minus phi x0 comma y0, which is equation number 5. The RHS of equation number 5, this shows the work done in moving the particle from p1, that is x0 comma y0, to p x comma y, whereas the LHS shows the change in kinetic energy of the particle. So the kinetic energy change is equal to the work done by the total external force. The equation 5 is the energy equation, and the forces of this type are known as conservative forces. The potential energy of the particle is given by the formula potential energy P equals integration from x comma y to x dash comma y dash x dx plus y dy, which is equation 6, where x dash comma y dash be the standard position of the particle and x comma y be the position of particle from when it moves to x dash comma y dash. Now let us study about central orbit. A force which is always directed towards a fixed point is known as central force. The fixed point is known as center of force. The part described by the particle under the action of central force is known as central orbit. Now, central orbit in a plane curve. Let the particle move under a central force MP with O as center of force. The force acting along AO. The equation of motion will be m d square r upon dt square equals minus mp. But force acts along the radius vector, that is minus r. Then r cross d square r upon dt square equals 0. That is r cross d square r upon dt square plus dr by dt cross dr by dt equals 0. That is d by dt of r cross dr by dt equals 0. On integrating, we have r cross dr by dt equals c vector, which is equation number 1, where c vector is a constant vector. Taking dot product of equation 1 with r, we get r vector dot c vector equals 0. which is equation number 2. Equation 2 shows that the radius vector OA is perpendicular to the fixed direction c vector and hence lies in a plane. Now let us study about Kepler's law of motion. So, first states that each planet describes an ellipse having the sun in one of its foci. The radius vector drawn from the sun to the planet describes equal areas in equal times. The square of the periodic time of the various planets are proportional to the cubes of the major axis of the orbit. The second law says that the aerial velocity is constant, or r square theta dot equals constant. Hence the force of the planet is entirely directed to the sun. From the first law, it follows that the force on the planet is inversely proportional to the square of its distance from the sun. From the third law, it follows, since t equals 2 pi upon under root mu into a to the power 3 by 2, that mu is a constant, that is, acceleration at unit distance from the sun is the same for all the planets. Thank you so much.